Hi everybody, today we are going to talk about some new techniques for evaluating limits. So what we've talked about previously is evaluating a limit using direct substitution. However, sometimes that's not possible. For example, if you use direct substitution and the denominator of a rational expression becomes 0, that's undefined. So we need to have some other ways to address this. So one method that we can use is we can look for common factors in a rational expression to factor out. Then sometimes the remaining expression we can evaluate using direct substitution. Another method we can try when we have radicals is we can try to rationalize either the numerator or the denominator, and this is by multiplying by the conjugate. Now this will give us a new function, or a function that looks a little different, and oftentimes that new function we can evaluate using direct substitution. And then, of course, if those methods don't work, we can always use technology. We can use a graphing utility to either evaluate the limit using a graph or a table of values. So let's try that first method, dividing out a common factor. You can see that since I'm trying to find the limit of this function as x approaches -3, if I use direct substitution, my denominator becomes 0 and it's undefined. So we're going to see if there's some sort of common factor that we can find. So let's factor our numerator. And you can see that there is a common factor of x plus 3. So that remaining expression, will have the same behavior as x approaches -3. Although it is a different function, it will have that same behavior, and therefore our limit will be the same. So this I can evaluate using direct substitution, and we get -5. All right, go ahead and pause the video and see if you can give this problem a try. All right, go ahead and check your work here. So here you can see that we have a common factor of x minus 4. If you divide it out, that remaining expression we can evaluate using direct substitution. All right, so let's try another one together. Here, once again, we can see if there's a common factor, because if we use direct substitution, our denominator becomes 0 and it's undefined, so we can't find the limit in that way. So let's try using factoring by grouping. So if I group my first two terms, I have a GCF of x squared. And if I group my second terms, well, I can just group it like this, x minus 1. So the limit as x approaches 1. Here, remember, if I have two factors that are the same, I can group the remaining two coefficients. So x squared plus 1 times x minus 1. I see that I do have a common factor. So this is now an expression where I can evaluate the limit using direct substitution. So this limit will be 1/2. All right, go ahead and pause the video and give this problem a try. Okay, so here once again we can factor by grouping. We can cancel out the common factor of x minus 7. In the remaining expression, we can find this limit using direct substitution. So we get 1/56. All right, so now let's talk about that rationalizing method. So here, once again, direct substitution doesn't work. Our denominator becomes 0, and there's no common factor to factor out. So let's see if we can rationalize, in this case, our numerator by multiplying the numerator and denominator by the conjugate. So the conjugate would be square root of x plus 1 plus 1. We essentially just make this sign opposite. Okay, so let's multiply this out. So when I multiply these two out, I get x plus 1. So we'll say the limit as x approaches 0 of x plus 1. This and this will cancel out, and then I have minus 1 over x times square root of x plus 1 plus 1. You can see that in my numerator, I have x plus 1 minus 1. So those will essentially cancel each other out. And then we can look for a common factor to divide out. I see I have an x in my numerator and denominator, so I'm going to divide that out. And here is what I have left. So this is something that we can evaluate using direct substitution. If I substitute x with 0, I end up with a limit of 1/2. Okay, go ahead and pause the video and give this one a try. So once again, here you can see that by multiplying by the conjugate, we have a new expression which will have the same behavior as x approaches 0. We're able to divide out a common factor, and then we can evaluate this limit using direct substitution. All right, so like we mentioned before, if you aren't able to multiply by the conjugate and you're not able to divide out a common factor, for now, all we can do is use technology. So if we have something like this is kind of an interesting limit that you'll definitely see again in calculus. Here you can see that I made a table of values and I graphed it. So the limit as x approaches 0 of 1 plus x to the power of 1 over x, if you look at as we're getting closer and closer to 0 from the left and closer to 0 from the right, you might notice that this is actually approaching e. So the limit of this function is e as x approaches 0. So go ahead and pause the video, use some sort of graphing utility to either make a table of values or a graph and see if you can evaluate this limit. So here's my Desmos graph and my Desmos table of values. So you can see that this one, as I approach from the left and from the right, or from my graph, this limit approaches 1. All right, so here's another kind of interesting looking graph. The limit as x approaches 0 of sine of x over x. So we end up with something that looks like this. So we can see that from the left, it's getting really, really close to 1, and it would do the same from the right. So this limit is also 1. All right, go ahead and pause the video and see if you can give this last one a try before we move on to a different topic. Okay, here, whether you're using a table of values or a graph, we can see that as we approach 0 from the left and from the right, our limit is 0. So these numbers are actually really, really small, so small that they had to use scientific notation. Okay, so now we're going to talk about what's called a one-sided limit. So we can actually describe the limit as x approaches c from either the left or the right. We can just describe one of those. So we know that if the behavior on the left and right is the same, then the overall limit exists. But sometimes even when the limit doesn't exist, it can still be useful to describe one-sided limits. So just make sure you understand the notation. So you can see right here, we have as x approaches c and then this little minus sign. This means from the left, and when you see something like this with the little plus sign, it means from the right. And then once again, if the left and right side behaviors match, then the limit exists. And if they don't match, then the limit does not exist. So let's try this problem. So here we have f of x equals the absolute value of 2x over x. So let's sketch a quick graph of this function. So if you make a few, if you plug in a few x values, for example, if you plug in positive 3, you get 2. And if you plug in positive 2, you get 2. If you plug in positive 1, you get 2. And we know that this would continue, except we know that x cannot be 0. So I'm going to draw an open circle at 0, but then it goes like this, and we keep going this way. But as soon as I start plugging in negative values, if I plug in negative 1, I actually get negative 2. If I plug in negative 2, I get, or negative 2, I get negative 2. If I plug in negative 3, I get negative 2. So it has an open circle again at 0, but then it continues on as a constant function moving to the right. or to the left. So I can clearly see here that the behavior on the left does not match the behavior on the right. However, we can still describe the limit as x approaches from the left and from the right. So the limit as x approaches 0 from the left of f of x, so this is our new little symbol right here. So let's see what's happening. As I'm approaching from the left, my function is approaching -2. It is a constant function, everything to the left of our y-axis. And then the limit as x approaches 0 from the right of f of x is just +2. So although there is no overall limit as x approaches 0, we can still describe the behavior from the left and from the right. Okay, go ahead and pause the video and give this one a try. Okay, so here, this is what our graph looks like. So you can see this is kind of like the switchover point. So while x is not defined at 3, it goes all the way up to there and then just has an open circle, and then everything to the left is here at -1. So as x approaches 3 from the left, our limit is -1, and as x approaches 3 from the right, our limit is +1. Okay, so now let's try this function. We have another piece, or we have a piecewise function here. So let's graph it. So although neither of these functions are technically defined at 1, we still want to know what would be happening at 1. So if I substitute x equals 1 into my first function, I would get 3. So I'm going to put an open circle at 1, 3. And then I know that this is just a linear function with a slope of -1 and a y-intercept at 4. So it's going to look something like this. And it's for all x values to the left of 1 when x is less than 1. I also would like to know what would be happening if I substitute x equals 1 into this equation. If I substitute x equals 1, I also get 3. Now I know that this is a parabola. You could take a second and you could actually find the vertex. So our vertex would actually be at 2, 4. It's a downward facing parabola, and it also has a an x-intercept at 4. So it looks something like this. Okay, so now let's describe the left limit and the right side limit as x approaches 1, and then see if an overall limit exists. So the limit as x approaches 1 from the left, that's over here, of f of x is going to be 3. The limit as x approaches 1 from the right, that's this, I can see that it is approaching 3. So since the limit as x approaches from the left matches the limit as x approaches from the right, the overall limit as x approaches 1 of f of x exists, and it is 3. All right, so go ahead and pause the video and give this one a try. Please take some time to actually graph this accurately. Make sure you remember how to find the vertex of a parabola and get a nice accurate graph. Okay, so here you can see this is the first part of our function. So as when x is greater than -1, we have a linear function. When x is less than -1, we have this quadratic function. The vertex is at -3/2, 9/4. But you can see that from the left, the limit is, as x approaches -1, is 2. From the right, the limit as x approaches -1 is also 2. So our overall limit is 2. All right, that is all for tonight. Thank you so much for watching.